Hey guys, I'm back with another video. This is going to be an either or constraint video. So I'm not going to explain what either or constraints are in linear programming, but I am going to explain the either or constraints in terms of this problem. So go ahead and maybe do some research on that if you haven't learned what an either or constraint is, because I'm not going to go completely into detail. And I do apologize if you hear my dog in the background. Anyway, so this is going to be from the textbook that I've been using in the past couple videos, and I will put that down below in the description. But I am going to try to summarize this video and also program as we go along through the problem. So basically we have three types of cars. We have compact, mid-size, and large, and we want to produce these cars. We have a certain amount of profit or profit yielded by each car and steel and labor requirements, and that is in this table down here. So we can see that each column is a different car type, and across is either the steel, labor, or the profit. And we currently have 6,000 tons of steel, 60,000 hours of labor, and we also must produce at least 1,000 cars of a certain type if it is produced. So in other words, we are going to have a binary variable in this problem telling us whether or not we want to produce that car. And if we do produce that car, we need to meet this minimum requirement. So, and then the overall, we are maximizing the profit in this IP. So let's just go ahead and jump into our decision variables down here then. We have X subscript, and each number is a different type of car. So 1 is compact, 2 is mid-size, 3 is large. And then our objective function is nicely written out for us. So they just took the profit for each car down here in this table, and they wrote it in thousands and multiplied by each decision variable. And then this is where our either or constraint starts coming into play. So if a car is produced, we must produce at least 1,000 of that car, and if it's not, then the amount of that car, of course, needs to be either 0 or less than that, because we aren't producing it. So these are our three constraints for each type of car. We either can be greater than or equal to 1,000 or less than or equal to 0, and then we have two more constraints, and that's our steel and labor constraint. So I'm just going to go ahead and start off with the sets and the parameters, and then I'm going to explain how we're going to set up these either or constraints. So you want to start off with from PuLp import, still using the PuLp packages I have been in all my videos. So let's call our set car, and we only have one set because we just have our subscript of the 3 cars. And you can call that car 1, car 2, car 3 if you want, and use a string, but I just want to keep it simple. So next we have our parameters. So we're going to make a dictionary for each parameter, and we're going to refer to this set. So the amount of steel required is 1.5 for compact cars, 3 for mid-size, 3 for mid-size, and 5 tons for large. What is my dog doing? Then we have our labor parameter. And then I also am going to write this profit parameter in thousands. And then we need to set our problem variable. So we do prob equals LP problem. And let's call this either or. And you can call this whatever you want. And of course we are maximizing because we want the max profit from this production. And the next thing, let's just go ahead and set this first decision variable. And it does say it's an IP, so let's just call this x underscore vars. I'm not getting sick. LP variable.dacts. It's just called x, and our only set is car, and let's say 0, none, and it says it's an integer program, so I guess we're going to call it LP integer. And we are going to have, again, like I said, a binary variable, but let me just go to this page and explain what our either or constraints are. So thankfully they kind of have them written out for us, and I'm going to explain what happens when y1 equals 0 and y1 equals 1. So basically what we are going to have this other decision variable. So y1 is whether or not we produce, what was it, the compact cars. So y1 is given the value of 0 if we don't produce compact cars, and it's given the value of 1 if we do produce compact cars. So let's say the program tells us we are not going to produce compact cars. What this means is that first of all, the x1 has to be 0 because we're not producing anything. So if you plug in a 0, this side is just going to go to 0, and therefore x1 must be less than or equal to 0, which we saw over here. And what happens over here is we get 1 minus 0, and that means this m1 value is going to stay. So basically, in other words, we need to make sure m1 exceeds 1,000, because if this x1 is forced to be 0, then on this side we're just going to have 1,000 minus 0, and therefore it'll be just 1,000. So again, we need to make sure whatever we set this value to, it has to be greater than or equal to 1,000. But in this, when y1 is equal to 0, this line is not really serving its purpose. So I'm going to explain what happens when y1 is equal to 1. So if it is given a 1 and we do produce compact cars, then this is going to be 1 minus 1, and therefore this whole side is going to go to 0. And what this means then is 1,000 minus x1 must be less than or equal to 0. So what that forces x1 to be, it forces it to be greater than or equal to 1,000, because if it was less than 1,000, let's say 1,000 minus 900, it wouldn't be less than or equal to 0. So that is where this constraint is fulfilled. And then in this case, in the first line, if we have y1 equals 1, this also makes there be a constraint that ensures that x1 is less than or equal to the max amount that it can be based off of our labor and steel supply. So it does tell us what that M1 needs to be based on the resources that we already have, and it tells us that x1 cannot be greater than or equal to 2,000. And then constraint 2 and 3 are the exact same, except we have different values based on the amount of steel and labor it takes and the amount that we have. So M2 is also going to be 2,000, and M3 is going to be 1,200. Hopefully I explained that so that you could understand it. But basically, again, these constraints are set based on the y1 or the y subscript variables. Then we have our steel and labor constraint. This is just exactly what you'd probably expect. We have the number of steel required for each car multiplied times our decision variables for that car, and it has to be less than or equal to 6,000, and same for the labor, it must be less than or equal to 60,000. And actually we are going to type this into the computer exactly like this. We don't need to rearrange anything. Sometimes we do if we have a value number, like if we have a decision variable over here, sometimes we have to adjust this equation, but because this is a binary number over here, or binary decision variable, we don't have to adjust it. And let's see how much time I have. I'm going to write the second decision variable and the objective function, and then I'm going to split this up into a second video. So go check that out. So we have our y variable, And again, this is deciding whether or not we are going to produce that car. So it's binary. And then prob plus equals, and we are summing over our profit times the decision variable. So we index the dictionary, and I'm going to use I since that's our first index value, and then we are multiplying times the x. That also needs an I. And we're going to create a loop for I in car. And that's all it is for the objective function. So pretty simple. Go check out the next video for the rest of the solution.